Is there any feature or way that intelligence manifests in biological organisms that can't be replicated or generated, or AI can't be put toward?
So to answer the question requires a clear understanding of how biological neural systems work, which we don't have. The best answer can only be a guess. But I think the answer is probably no, there's nothing special about biological systems. That'd be my best take on it from what I know. It is not true that an infinitesimal multiplied by an infinite results in some finite number. It could be that the infinitesimal is so darn small that even if you multiply it by a vast infinite, you still end up with zero or one,
Well, yeah, it
rather
would
than
have
multiple.
to be non-zero.
Yes, well, because we have one example of an intelligent
Yes.
species, we're sitting here.
Could an artificially intelligent entity solve moral problems?
Okay.
That makes one assumption, and that there's a moral fact. In other words, that there's something to be known about morals, and you can figure it out.
Yeah, and in fact, I would suggest it makes an even deeper assumption, which is that the quantity you're trying to measure can be mathematically and precisely quantified.
Right.
I know whether a series of moves wins the game or not. There's no question about it. I know whether a fold of a protein will produce a certain energy level. These are deterministic, mathematically precise problems. So for those kinds of problems, we can reach computationally exact conclusions. But when it comes to moral questions, the issue is, how will you measure right or wrong?
I think that should give us courage, exposure to other people's perspectives.
Moving us in a good direction. Welcome to Conversations with Peter Boghossian. I just had a fantastic conversation with Clint Staley. He's a professor emeritus at Cal Poly and a professor at Principia College in computer science. And we talked about a wide range of issues, from the Fermi Paradox to neural networks to artificial intelligence to science fiction, my favorite subject or one of them. Hope you enjoy the show. Thanks. Clint, welcome to Conversations with Peter Boghossian. Thanks for coming to Denver to have a conversation with me. Tell us a little bit about yourself for those of us who are not familiar with your work.
Sure. Well, I'm a professor of computer science, and I spent most of my career at Cal Poly in San Luis Obispo. And my own focus has been teaching, of course, at a school like Cal Poly, but also the interface between academia and industry. So I've had involvement in software development with, goodness, at least a dozen different companies, big and small. Done a few small startups of my own, nothing huge, but good experience. And I'm particularly interested in getting sharp students involved in challenging industrial opportunities while they're still in school, which, for instance, is something that UATX, I know, is interested in doing through its Polaris projects. I think that's a great idea. A lot of kids are ready for early challenge, and I've hired hundreds of computer science students and gotten them involved in industrial work in startups and larger companies. I think it's a great idea. So,
Okay, so there's a lot to unpack in that.
Sure.
One of your specialties, correct me if I'm wrong from what I've read, you've written, is AI.
I'm certainly involved in teaching AI. I don't pretend to be a world-class researcher in the subject area, but I started teaching it in the 1980s when neural networks first had their resurgence.
What's a neural network? Tell us.
Okay, so the modern AI we're looking at is built on an idea that originates back really in the 1950s even, trying to simulate the way a brain works. And roughly speaking, your brain's a connection of neurons, and each neuron has multiple inputs, chemical inputs from other neurons that feed it or stimulate it. And once it is triggered to a certain point, then it in turn triggers neurons downstream of it in a sort of network chain. And the interconnections between neurons, called synapses, are different and determine to some degree the way one neuron influences another. So the amount of influence that one neuron has on another neuron is determined by its synaptic strength. So from fairly long ago, again, 60 years ago, there was a thought that we might try to model this behavior in a more mathematical way. And it's easier with a diagram, but basically a neuron in the AI sense is first a software entity. And they used to do these with actual hardware pieces, but it's long since become a software concept. And what we do is have input from other neurons in the program, weighted mathematically. So maybe neuron 1 communicates to the next neuron with a weight of 2 Everything it says is multiplied by 2. A different neuron inputting might have a weight of 3. It's more important. Still, another neuron might have a negative weight. It's -5. And the combination of weighted inputs from the neurons that feed you are summed up by the neuron that is being fed, and then it produces an output from that, which feeds other neurons in the next level down. And so it goes.
That's a neural network.
And that is a neural network, a series of layers of these neurons, each layer having weights from each neuron in it that determine how those neurons influence the next layer. And each neuron in the next layer takes the inputs from the layer above and sums them up according to the weights, and that determines its behavior. And an element here that might be worth noting as well, because it has some interesting philosophical properties even, is that one of these neurons, after having summed up all those inputs, this guy times 4, that guy times -1, and so on, takes the sum and then further processes it. There's something called an activation function. And that doesn't have to be a super fancy thing. It can be as simple as a rule that says, well, if the total is negative, what that means is I'm not important. And I'm not going to put a negative out. I'm just going to put a 0 out. And if it's positive, then I'll put out the positive value. Or it can be more complicated. It can be, well, if it's negative, I'll put out a -1. If it's positive, I'll put out a +1. And I'll switch between the two as it gets near 0. And so this activation function is also part of the game.
So I play chess sometimes on my phone. I'm not very good, but I set it at the highest level and it crushes me. It feels like I'm drowning. But it gives a thin lines depending on their thickness. Green thick is this is the move. Green thin is less good of a move, and like green barely a line is eh. Is that similar to a neural network?
No, and I don't know the program you're using per se, but generally the chess programs you're playing are using an older form of artificial intelligence that does a systematic exploration of the game move tree, the kind of thing you do when you're playing chess. If I do this, and then he does that, and then I do this, what's the outcome going to look like? It's doing that kind of look ahead, an algorithm called Minimax. And it doesn't have anything per se to do with neural networks. I suspect what's happening with those lines is that that same algorithm can judge the goodness or badness of a move based on whether player 1 or player 2 is going to win, and give you that judgment call, that mathematical determination in the form of thick lines. And that's probably what you're seeing there.
So what does one do with a neural network? Like, does it answer a question? Is it like a large language model? Like, what do you do with it?
Okay, so it's a pattern recognition tool. And what that means is that you can present the first layer of one of these networks with a pattern, and we'll get more specific about what that can be, but very briefly, it's a set of numbers, what mathematicians would call a vector. So you can present it with a pattern of 100 numbers. And then the first layer processes those as their inputs, feeds into the next layer, which does its processing, and the next, and the next. Finally, at the bottom out comes another pattern of numbers. And in a very rough description, that's all it does is convert input patterns of numbers to output patterns of numbers.
And to answer a question,
so
play Go.
What can you do with an input pattern of numbers is the interesting question. So what can that mean? Well, for instance, if it's an image, I can boil an image down to a sequence of numbers. I simply take every pixel in the image. If it's a black and white or grayscale image, then a value between 0 and 256, 255 will describe one of the pixels. 0 black, 255 white, anything in between gray. If it's a 100 by 100 image, that's 10,000 numbers. And so I can feed the image in as 10,000 numbers. That's its input. And then the output might be categorizing what's in the image. Maybe it's supposed to identify a face. And we have 100 different faces
so that's
possible.
the network, not the, I see, okay.
So we feed in the picture. Yeah. And outcome at the bottom will have 100 numbers. And those will be the probability that the face is Peter or Clint or someone else. Yeah. And those can, in fact, be different probabilities for each person, so that it can say, well, I think there's a 95% chance this is Peter, but there's a 5% chance it's Reed, and you have a 1% chance. Well, that wouldn't total to 100, but you get the point. It can give you the percentages of likelihood, and that's a categorization use of a neural network.
Okay, so I think I have a very, very rudimentary understanding of it. What do people mean? Is there an agreed upon definition when someone says artificial intelligence?
Good question. No, it is a very fluid term, and it usually means programming a computer to do something that you don't think computers really are able to do and is more human-like. And what that, of course, means depends on when you're talking. So the very idea of a computer that might play chess or even checkers in the 1960s would have been considered artificial intelligence, because computers did computations maybe, but they sure didn't play checkers. And so the idea that you could code a program to do that was heading toward intelligent behavior as we would understand it, and would have been characterized as AI at the time. But that's become commonplace now. So most people would not call chess playing serious AI. It's a moving target, and it generally boils down to doing stuff that should be, or you would expect would be only doable by a human.
Okay.
Having an intelligent conversation, or even a reasonably intelligent one, is something we thought only people could do 5, 10 years ago. And now we're talking to large language models or ChatGPT, and it's just like talking to a human being, and that's pretty surprising, and we didn't think computers could do that, so that's AI.
Okay, so when someone says intelligence, usually I think of intelligence from an evolutionary perspective, an adaptive perspective. So like, Jane Goodall's orangutans that use sticks to pick things. So is it, what do we mean by intelligence? Like, what does that mean? Like, what does it mean?
It's a good question, and I think there are a lot of different definitions, right? Being able to recognize patterns, faces, objects, sounds is an intelligent behavior. We think of it as somewhat automatic, by the way, but you use a good portion of your brain recognizing patterns. You're just not conscious of it. So that's an intelligent behavior. The ability to use language is usually characterized as an intelligent behavior, to work with symbols and to think through reasoning processes and so forth. I don't know that there's one good mathematical definition, but all these things.
Correct me if I'm wrong, I'm thinking out loud here. So the ability to make inferences from a data set or to recognize faces, that seems like one level of intelligence, although somewhat categorically distinct. Could we say that there's a hierarchical order of intelligence in which, for example, lying, something that goes against one's programming, would admit of more intelligence than facial recognition technology?
Interesting question. I suppose it depends on how smart the lie is. But I don't know that there's a strict way you could describe one thing as significantly more intelligent than another. It's also worth noting that when it comes to programming a computer to do stuff, which in a sense you might think of as a fundamental yardstick of how hard something is intellectually, because you've got to boil it down to fundamental pieces to do that, right? What we consider hard intellectually is not always the same as what a computer finds hard, or what a programmer writing code for a computer finds hard. A good example is chess playing. We think of that as a very high skill, but it turns out that it was easier to code than facial recognition, which we think of as a routine skill. Maybe we have a little trouble with it, but it's not high intellect. And I think part of the reason for that is that some things we are, as you say, by evolutionary process, instinctively good at. Recognizing faces is important if you're going to get along in a social circumstance. So a significant portion of your brain is used for that kind of thing. You're just not conscious of it. And so you tend to think of it as not that sophisticated intellectually, where in fact, if you try to program a computer to do it, it's harder than chess.
Why was it harder to program a computer to win at Go than it was at chess?
Okay. And so what you're referring to is the recent development where AI of the modern sort, something called reinforcement learning, was used to produce a program called AlphaGo that famously beat the best human players at the game.
That's
I think it's about 5 years ago now,
what
something
I'm
like
referring
that. Right, okay. So you got to think a little bit about how you do a systematic analysis of a strategy game like chess or checkers or even something as dumb as tic-tac-toe. What you have is some programmatic representation of a board. What's the current layout of the board? Initial chess position or just an empty grid for tic-tac-toe? And then moves you can make from there. And you can almost envision a sort of tree. For tic-tac-toe, it's not too hard. You start with an empty board, and there are 9 possibilities, right? 9 places you can put the X. So 9 new boards come from that. And then from each of those, 8 more possibilities, because you've already occupied one square,
yeah.
you've got 8 more to go.
Yeah.
And you can imagine that going out as a large tree, right? And it would be big, but you could draw the whole thing out if you had enough room and a tedious afternoon to do it in. At the end of the tree, at the bottom, you know who's won or lost. It's a conclusive figure at that point. And then it's not hard mathematically to work your way back up the tree and say, well, okay, if at this point all the options that could be played either result in a tie or X wins, and if it happens to be O's move at this point, they're going to choose the tie.
Oh, so maybe this is an example of making an inference that's wrong, thus I'm less intelligent. So you're saying there are more permutations in, is that the correct inference?
Yeah, we're going to get there. And
okay.
You're on the right track. That's where it's going to head. So if you analyze one of these trees, for chess, it's way too deep. You couldn't draw the whole thing out. So the program approximates. After a certain number of moves, it just looks at the board and says, well, you got more pieces than I do, does point count, position strength, and says, okay, I estimate that black is winning here. And we work the tree that way. We don't go all the way to the end because we don't have that kind of depth. So 2 things come into play here now. How many branches are there at each step? How big does that tree get? That matters. How far ahead do you have to look before you can make a smart move? That matters, because the tree can't be pushed too far down before you just have to estimate. For chess, you can do a pretty good job and get a tree of, goodness, I think a dozen or more levels is not uncommon now with some optimizations thrown in, right? You'd have to check me on that. But for Go, the game is played on, I believe, a 19 by 19 board, and you can place a stone anywhere in there. 19 times 19 is nearly 400 positions. So right off the bat, there are 400 choices, and then 399 and 398. So it's a huge branchy tree. And the way the game is played, there are patterns of play where you can't really know what's going to happen until about 20 moves later. Okay. And a good Go player can say, if we race to the edge, I'm going to beat you here. But it's going to take back and forth for 20 moves. So that depth of analysis is also needed. And the combination just killed the algorithms that were used for chess. They couldn't handle Go.
So what is it that's preventing us from, quote unquote, solving chess? By that I mean, there's a perfect move that one can make. In other words, there's a telos of strict move. Is it raw processing power that's preventing? I mean, if you had a computer of, from 100 years from now, super AI, whatever, it would seem to me would be able to solve chess.
Okay, so now you're talking about solving a game.
Okay.
I think there's even a German word for it, game death, something like that. And
there's a German word for like everything.
Yeah, there is, isn't there? Yeah. Germans are good at compound words with interesting significance. This is obviously the case for tic-tac-toe. Anyone who's played the game knows that if you play properly and each side does the right job, it's a tie every single time. So the interesting question is...
chess death. Yeah, anyway, go ahead.
The interesting question then is, what about a more sophisticated game?
Yeah.
Is chess ultimately tic-tac-toe? If both players play perfectly, will you always have tie after tie after tie or not? The process of solving that, as you imply, is very computationally difficult. It depends on how sophisticated the game is. It depends on how clever your algorithms are, because this tree I'm talking about, there are clever ways to avoid having to explore parts of it. I won't get into the mathematical details. It's an hour-long lecture in an algorithms class.
I wouldn't understand anyway.
I think you probably could if we went through an hour, but you don't want to do that on a podcast here. The point is that you can optimize this process, and if you're clever, you can cut down on the work. But still, it's ultimately a question of fully exploring at least a good portion of that tree.
Okay.
This has been done for checkers.
Okay. So
checkers was solved, I think it was about 20 years ago now. And I believe the result is first player wins, but I'm not sure. It might be tie. It won't be second player, right, because they have an automatic disadvantage. It's not been done yet for chess, but there's nothing to prevent that in the future. I mean, it will happen sometime.
That is not a philosophical question. It's a technological question.
Right. There is certainly a outcome if each player plays optimally, given that chess is a fully and exactly defined game. There is certainly either a tie that will result if each player plays perfectly, or possibly white wins since white is first player. Same goes for Go or any other abstract strategy game. So from a purely ontological standpoint, if you want to use a philosophical term, yeah, there's a definite answer. We just don't know what it is, at least for the more sophisticated games.
And that's just a matter of processing power and the quality of our algorithms.
Yes.
But the quality of our algorithms can be increased by artificial intelligence.
Yes. And what is going on in the Go game, for instance, with AlphaGo, is that it is not exploring the tree fully. That's too hard. What it's doing instead is what a good player does.
Interesting.
A good Go player is not quite thinking like a chess player. They're not doing the move, counter move kind of reasoning. Instead, they have a pattern recognition ability. They know how Go will turn out with this pattern or that pattern. Even looking ahead 20 moves, you and I race to the edge of the board, I'm going to win. And we both know that, and we might not even try because we know what that outcome is going to be. And we're doing experienced pattern recognition. And it is more reliant on that very intelligent human capacity. That's why it's regarded as such a sophisticated game. I mean, most people would say it's more sophisticated than chess.
Oh, for sure.
Yeah.
I was on the chess team in college, and people used to come and bring their Go boards. And I mean, it was incredibly difficult for me.
And for such a simple set of rules, too, it's quite remarkable. So what you need to do is design one of these neural networks that can take an input pattern, which is a Go board. And we have a number for each cell. This is the Go board position. And then an output pattern that says, here's where you should put your stone. And then train it by experience so that for a given Go pattern input, it makes a good judgment as to what the next position of a stone should be.
And does it subsequently analyze the games that it won and lost? Is it like a repository or a database where it sends those and it analyzes those?
Yeah, more than even that. It analyzes millions of games that it's won or lost. And this is how it was able to do this. Going back to our neural networks.
Please.
How do I adjust a neural network so that it does the job we're describing correctly? For faces, how do I make those intricate sets of weights so that when I present a picture of your face, it says Peter, and in my face, it says Clint, and so on? It's all about the weights between the neurons and their connection. And how do we adjust those weights to get this kind of intelligent output? And the answer is we use an awful lot of examples. So for a neural network that does what we described in face recognition, it would be helpful to have hundreds of examples of your face and mine, maybe even taken off of a video where we get maybe 24 frames a second or 30 a second, and looking at all of those examples and learning from that. For Go, we're going to need a lot of Go boards and a huge amount of training data to know what the right move is, okay? How do we get that? That's one of the big challenges in modern AI, is having enough data to train it well. And it needs, it's very data hungry, needs a lot of information for us to adjust those weights properly to get the intelligent behavior. One way to do it, when we have a definitive game like Go or chess, is to do what a human player will do sometimes, which is play against yourself. And you may have tried this as a chess player. You move for white, and then you do your best job for black, and your best job for white. And you're playing both sides, trying to do the best you can for each side. And from this, you learn. You say, oh, well, I made that white move, and that kind of sucked because 2 moves later I lost my queen. And you get a sense of the right thing to do in different chessboard positions simply by playing all by yourself, right? This is, in essence, what AlphaGo does. It learns by playing Go against itself and running Go game after Go game at multiple billions of computations per second, so it can do this lightning fast, and producing a whole lot of information about Go boards and about what moves were good and what moves were not. And it's a form of AI called reinforcement learning. Anytime you can set up a model where you can play the thing over and over again, whether it's a game or other things we'll talk about, you can get a lot of data. And you can train a neural network effectively if from that data you can get information on what input pattern should result in what output pattern.
Huh. Okay, so talk to me about reinforcement learning.
So that's the process we're describing here, where we satisfy the need for example input-output patterns by doing some sort of play against yourself automatically. It's not always usable, but where it is usable, it's enormously powerful. And one of the stories that I think doesn't get as much attention with modern AI, everybody's so fascinated with the ChatGPT and the large language models, and they are fascinating.
Yeah.
And you're talking to something that seems human. But there are a number of other areas that are under development that are producing some remarkable results, and they're not getting as much attention. And RL, reinforcement learning, is one of them.
What is that?
So it's, again, anytime you can set up a model where you can have the system play against itself or try a problem in random ways to see what works and what doesn't, you can generate very rapidly huge amounts of sample data and then train a neural network or a deep learning network, which is not quite the same thing, to do this pattern recognition. Okay? AlphaGo is an example. In fact, I understand, and I haven't read the details in this, but I understand they took the same tool and tried to use it for chess. And it, I think in the course of an hour or so, blasted through so many chess games that it taught itself to play the game and became better than just about any other tool, program, or human that played chess in
I
an
haven't
hour.
heard that. Wow.
Yeah. That's how powerful the mechanism can be. Now, it's touchy mathematically. It's got some problems. When you do a series of moves and you win the game, the question arises, which move was the right one? Because they're not all smart necessarily. Some of those moves might have been dumb, and maybe it was just the particular move you made with the queen at the fifth move of the game that really made all the difference. So there's some mathematics surrounding how, in a series of moves, do we pick the ones that were really the exemplars that we want to train on. All right? And there's also the problem, as would be the case if you played yourself. Maybe you learn a strategy and a way of doing it, and you find that kind of works. Well, you'd be inclined to try that again and again and refine it better and better. But the problem is there might be some brilliant alternative strategy that you didn't learn. And so it's easy to get captivated by your own learning and not exploring. There's a balance between refining what you already know and trying the new. And these systems even have a hassle that comes up in training them called catastrophic forgetting, which is you'll train the thing and it will start getting really good, and then suddenly it just sucks. And the reason is it started exploring a different line of possibilities.
Interesting.
Came up with new stuff. And just like a human athlete who's learned to hit the ball a certain way and they should have tried a different way. And for a while when they're adjusting to the better way, they kind of suck.
We need those we need those, right? Because that all factors into the modeling.
Yeah. And there's this is more than just a qualitative thing. There's some very strict mathematics called Q-learning surrounding this whole idea of how do I do this automatic play and then pick the right moves and the right balance between reinforcing what I already know and trying new stuff.
Yeah, it's interesting. I was just having two thoughts in the conversation. One is, what if you had some kind of catastrophic learning, but eventually it swung up again and solved the problem? Would the line of thought be dead? Like, at what point do you know to exhaust the line of catastrophic learning?
So at what point is it not worthwhile exploring other directions because you've kind of, we tried, but that really didn't work? It's part of the math. And some of it is a judgment call sort of thing. There's no exact proof. But in general, when an RL algorithm is operating, this is part of the decision it makes. Do I explore this line further or not?
So nothing that you've talked about today, in fact, by definition, is limited to the property of biologics, biological organisms. So
no, not at all.
Is there anything, I have two questions. My first one, is there any feature or way that intelligence manifests in biological organisms that it doesn't or that can't be replicated or generated or AI can't be put toward?
So to answer the question requires a clear understanding of how biological neural systems work, which we don't have. The best answer can only be a guess. But I think the answer is probably no, there's nothing special about biological systems. That'd be my best take on it from what I know. By the way, before we digress there, reinforcement learning. Have you heard about AlphaFold? Okay. You understand what it did?
No.
Okay. So the problem of folding a protein has been a standing scientific challenge for decades. Protein's a series of amino acids, right? G, A, T, C, that sort of thing. We can determine the sequence of acids that make up a protein. We've been able to do that for about 20 years now. We do it very inexpensively. But that's only the first step. Then the question is, how do these atoms in the configurations they have fold together? They have an attraction to one another. And that determines the ultimate shape of the protein. It folds into a complex ball of atoms. And the shape determines its biological function. Not the sequence of acids. Those just determine its shape. The shape determines the function.
Okay.
So the question then is, well, can I give you a sequence and can you tell me the shape from that? Well, it's a really hard thing to do. And it had been insoluble for years, except for a few breakthroughs, a handful of proteins after years of research, really important ones, like maybe insulin and that sort of thing they'd analyzed. But there are hundreds of thousands of them they couldn't solve. They trained an RL system to do it. And what it did was try to fold proteins and teach itself what patterns of fold would work and what would not. In essence, like playing Go against itself, except it's playing protein fold against itself.
And it tests it against actually doing it, or does it test it
You
against...
can know the outcome of a fold and the
so that makes
energy,
it-
the potential energy
You
that
can
results.
expedite it as a consequence.
Yeah, it's able to get its own feedback loop. The mathematics is well enough understood. The question is, which fold will get you the result you're looking for?
Right.
You know what the result will be from a fold, but there's so many possibilities that you can't determine the best one that will produce the lowest potential energy, which is ultimately what the protein tends to fold itself to generally. This thing now has solved hundreds of thousands of proteins. My understanding is that when they presented it a few years ago, there were researchers who'd been in this field for years who were devastated because they'd spent all their time trying to do this, and suddenly this problem that had stood as an insoluble for decades is being blown away by the AI.
Why would they think it's insoluble? It's just computational.
Okay, but does that mean soluble? It is not true that just because something is computationally unambiguous that it's easy to solve.
Well, not easy to solve, but theoretically solvable.
Okay, theoretically solvable?
Yeah.
Sure. If you have 100 million years to run it on, okay, there are well-known algorithmic problems that exhibit what is called exponential complexity. What that means is the bigger the problem gets, as you increase the size of the problem with each step, the amount of time it takes doubles.
Yeah, because the variables are multiplying effects.
Right. You have that kind of combinatorial explosion. In principle, you could solve it anyway, but you're going to need God's own computer in 1 billion years. So in practice, the answer is no. Just because a thing is computationally unambiguous does not necessarily mean, even with a modern computer, you can solve it. And protein folding was in that category.
But it does mean it's theoretically solvable.
Yes.
Okay.
But as they say, the difference between theory and practice always correspond in theory, but they never do in practice.
Right. Right. So, okay. So, listening to this, I have many things running through my mind.
The one thing I would leave with that thing, playing Go is great. I mean, that's nice. It's clever. Solving an important medical problem is a whole nother matter. And so this AI has contributed a big scientific advance. And it doesn't get as much attention. And now they're using it to try and design proteins to fold in particular ways for medical purposes, or design new chemical structures, new materials. There's a whole spectrum of very important scientific advances that may be coming out of reinforcement learning that are a little bit eclipsed in the public eye because the chat GPT is getting all the glamour.
It's more usable by ordinary people. In fact, we use it to debate people who won't debate us. We're going to do a series of I'm going to be debating ChatGPT as somebody. Okay, so
yeah, have you asked it to tell you whether it's intelligent and self-aware or not?
I have. Reed
done
and
that.
I have fooled around with it, but we're going to be. I had a interesting debate with ChatGPT, but one of the things I realized that I don't want to go down this rabbit hole, but the initial prompt is so important. So we're going to prompt it to be an expert debater with ample literature and empirical knowledge at its fingertips, et cetera, and then I'm going to debate it.
Yep.
Okay, so at some point, is it merely a matter of computational power before sentience is attained?
Good question. So now you're heading into what is sometimes called philosophically, as you mentioned a little bit ago when we were talking aside, the hard problem of consciousness. So how can I know whether an entity, say you, behaving intelligently, in all respects apparently intelligent, is actually self-aware, right? And that is termed the hard problem of consciousness. And the answer is nobody really knows. It's not something you can easily make a conclusion about. It has been debated in philosophical circles, as I'm sure you know, for millennia in one form or another. And the only logical way to say that I know you're aware that there's somebody in there, as opposed to the lights being on but nobody being at home, is by induction. I know I'm self-aware.
Right. Okay.
You're like me, so you're self-aware. But induction is not a notoriously reliable way of reasoning about things. So we're not really certain. We do this by intuition and induction. We assume that one another are aware, but you can't prove it.
Okay, so I want to rewind the conversation just a little bit. I've read Chalmers, I've read Dennett, and that's a whole other conversation. I'm happy to have it, but I want to make sure that I understand what we're talking about. So let's go back to the game of chess, please. It is my understanding that I don't know, fairly recently in the last 15 years, I don't know if you want to call it AI or whatever term one would want to use, that what we used to think was a stalemate, I think is a rook, a bishop, and a knight or something. I can't remember exactly. We figured out that that's winnable. AI figured out that it's winnable, and then they changed the rules. Okay, so
It did something similar with Go, by the way. It came up with some strategic moves.
was it move 73 or something like that? Yeah.
It
Okay.
came up with a completely new strategy.
Okay, so this is going to be a weird question, so I'm just throwing that out to you. In the same way that there's a truth of the matter about chess, and that truth can be solved computationally. For example, we figured out that no, this is actually not a draw if you do these incredibly precise moves, and I can't remember what it is, X number of moves later, we know that independent of how the other person moves, we know what the win condition. We know the win condition, and we know this person will win. Can we take that same sentiment, if you will, behind chess and apply that to other problems? Can we say, well, we don't really know the answer to this, like I'm thinking in the ethical domain or the moral domain, but perhaps at some level of reasoning which we don't have, which an artificially intelligent entity would have, or maybe if we just accept by fiat that that's possible, then could an artificially intelligent entity solve moral problems?
Okay.
That makes one assumption, and that there's a moral fact. In other words, that there's something to be known about morals, and you can figure it out.
Yeah, and in fact, I would suggest it makes an even deeper assumption, which is that the quantity you're trying to measure can be mathematically and precisely quantified. I know whether a series of moves wins the game or not. There's no question about it. I know whether a fold of a protein will produce a certain energy level. These are deterministic, mathematically precise problems. Likewise, Go. So for those kinds of problems, we can reach computationally exact conclusions. But when it comes to moral questions, the issue is, how will you measure right or wrong? Or if you want to address this consciousness problem or awareness, sentience problem, how do you measure sentience? I can't put a meter on your head and get a little sentience register that says whether you're there or not.
So
it's not something that this technology is really suitable for.
Let me see if I can answer that question. You tell me if my answer is satisfactory.
Okay.
And honestly, I don't take these things personally. In fact, just please really push back on me on this.
Yeah, no problem.
I'm just semi-spitballing it here. So I'm not sure the right metric would be how we knew it succeeded, because that would give away, embedded in the idea of success would be the method that got you there. What if instead you looked at it syllogistically? What if instead, because you can look at it syllogistically in terms of mathematical rigor, you constructed a genuinely elaborate syllogism in which I realize this might be a little tricky, but in which the premises led to a sound conclusion, but the syllogism was valid. Wouldn't that be a way to figure out if there were entire lines of ethical reasoning and moral thought that eluded us that an AI could shed light on without having to resort to the cash value. In other words, without having to resort to the outcome. You could just look at it in the same way that you looked at a mathematical proof.
Okay. So, talking mathematically, what you're describing by syllogistic logic
Correct.
is Boolean algebra. And
Correct.
it's
That's exactly what I'm talking
a
about.
well-established form of AI to take known facts expressed in mathematical terms, proving mathematical theorems is an application for this. And then by virtue of logical mathematics, Boolean algebra or syllogistic logic, if you like, reaching newer conclusions from that.
Correct.
Okay? But two things worth noting here. First, all logic systems are not means of arriving at original truth. Even mathematics requires a set of axioms, unproven a priori truths. And so one question is, well, what a priori truths will you begin with for your moral reasoning chain? And how do you know they're true? Logic and reason do not produce original truth. They produce derivative truth from assumed bases. Even the pure logic of mathematics is subject to this limitation. You have to start with a set of axioms, and from there you prove. Now, given that, you can arrive at very exact final conclusions, and there are famously, for instance, some mathematical proofs that have been done by computer, the kind of process you're talking about, an elaborate series of if-thens and logical conclusions, for which, as I understand it, the proof has never been actually followed by a human being. It's too intricate. So,
okay, well, that's the second question. Sorry, so that was my next question, but can we please not go there just yet? Because I do want to talk about it because that's a whole nother...
Sure.
Go ahead.
So the second thing, though, is that the outcome of a mathematical proof is a clear quantitative result, right? This combination of integers will produce a prime number, or I color a map, the proof I was mentioning earlier, I can always do the map with at most 4 colors. That's a very definitive, binary yes-no kind of outcome. I don't think that ethical and moral reasoning falls in that category. So even if I could start with a set of axioms about moral truth, derive from them new moral truths, I'm still dependent on the axioms, and the things I can derive still are subject to human evaluation. Is that result something we agree is morally good or not? The moral good, in other words, is not a mathematically quantifiable thing. And so I don't know that the kind of thing you're describing would work in moral reasoning, except perhaps to find some interesting line of reasoning that then a human could explore further. But in all that I'm aware of in philosophical moral reasoning, the challenge is never about whether we can follow the logic. The question is the axioms you start with, right? And whether you think those are good or bad.
So
and what constitutes the moral good, right? What's your ethical model? Is it pragmatic? Is it one of the other ethical models? What is your ethical model?
Am I correct in that the argument there is that a computer, artificial intelligence at no level of sophistication can give us a reason for those axioms?
For the axioms, no. Neither can you or I. If you start with a certain moral axiom, by definition, an axiom means an a priori truth, one accepted without any proof or prior backup, right? And all systems of reasoning have some like that. You got to have something to start with.
So I want to make sure we stick to the conversation to your domain of expertise. But with that said, just real quick, this is jumping out at me. Wouldn't that mean, however, that we lived in a moralistic, a universe that was morally relativistic?
It depends on whether you accept that the axioms in question are relative or themselves absolute.
Well, how would you know that they were absolute? You'd have to resort to something other than reason, or you'd have to resort to something like revelation.
I suppose that's a fair, I don't know if revelation has a certain religious connotation to it. I don't know it has to be a religious thing per se, but I do think that, yes, ultimately you'll have to start with some moral axioms. And if you're going to reason about moral things, you can argue that they are absolute. But there's no proof that you can offer for that.
Couldn't it also be that the starting axioms, if you fed in starting axioms to a superintelligence, it may not necessarily be the case that the moral pronouncements it would generate from that are rationally derivable from those axioms.
Well, I suppose it depends on the nature of the superintelligence, but if it's following strict logical processes, then there would be a clear logical path from the axioms to the moral conclusion. On
That
the other hand,
assumes
if it's
that-
engaging
yeah.
in pattern recognition, which is
Yeah.
a little sloppier,
Yeah.
then no, I don't think you could say that a pattern recognition system trying to make moral decisions will do so with perfect reliability.
Doesn't that assume that logic is the way to get to the moral conclusion from the axioms? Maybe logic goes out the window when you're talking about things in the moral realm.
Well, it's more your area than mine.
Yeah, well, I know that's why I want to stick to yours, but I was just thinking about it when we were having our conversation. So,
I think to be a little technical about it, exact Boolean algebraic or syllogistic reasoning remains a gold standard for arriving at truth from other truth. And AI doesn't change that. So the pattern recognition we're doing in AI is approximate. And if instead it could be replaced by a perfect moral or any kind of logical reasoning, if I could decide whether the picture is your face by precise logical rules, it's going to be more reliable than a pattern recognition system. The difficulty is that we can't do that. The problem is too complex to be subjected simply to pure logic. In fact, there was a period in AI development in the 70s and 80s when it was thought that we could do artificial intelligence this way. We could set up if-then logical rules about the world,
right.
and then from them make conclusions. The technical term for the kind of programs that did this was expert systems, and they would be used for instance, predicting the particular hardware needed for a given customer. One of the computer companies had a successful one that did this based on the customer's requirements, and if it's this, then that, and if that is there, then add this in, a series of rules that were quite syllogistic. Medical diagnosis possibly tried the same sort of thing. Limited success. Turns out that patterns are more complicated than that, and you can't boil them down to pure logic. Not that they couldn't be boiled down necessarily, but in practice, it's not possible to do so with the computing ability we have. And so all of AI took a different line, pattern recognition, instead of pure syllogistic logical reasoning.
So, kind of a curveball question, I think, maybe. Do you think, and there's just so much embedded in this question, it's just so radically speculative. Do you think that the creation of artificial intelligence is the telos for every conscious, rational civilization?
Well, telos implies a predetermined purpose.
Correct. That's exactly why I used it.
Right, yeah. But a more answerable question might be, will any sentient civilization probably arrive at artificial intelligence at some point as it develops its technology? And there you have to look at the whole idea of the history of technology and how innovation works. But a strong argument can be made that the pattern of innovations has its own momentum, that as new innovations arrive, they make other innovations possible in a sort of wave front of innovation that would be roughly the same even if different innovators had been involved. If Edison had died in his crib, we'd still have electric lights. It would have been invented by somebody else 6 months later.
Right. So
its time was there, and
Okay.
the necessary pieces were there. The same argument can probably be made for artificial intelligence.
So that's my question too. Have you ever played the game Civilization?
No.
Well, there are technology trees.
Okay.
And in order to get to one technology, you need a prior technology, and then you know prior technology. And it's interesting to me, because we have an N of one, we don't really know, that a spacefaring civilization. Do you ever watch Star Trek?
Sure.
Oh, good, you're not dead to me. That's good. You know Zephram Cochrane, the inventor
I'm
of...
glad you're a fellow Trekkie.
That's
cool.
good. That's more than you know.
So
All science fiction. I'm a science fiction fanatic. You know, Zephram Cochrane with the advent of the warp drive, and then the other species kind of. I wonder if there's something. Two things. First, I'll finish the thought. I wonder if there's something in which AI is commensurate with the development of spacefaring civilizations. Just a thought, because we only have an N of 1 because we don't know.
Right.
And the other thought, well, let's just go with that one first.
Okay. So probably the broader question you're really getting at is the evolution of technological ideas and innovations comparable in any expectable civilization, right? By the way, there's a useful term here. The idea that there is a body of existing innovation which makes possible
Yes.
the immediate innovations surrounding it.
Yes.
It's called the adjacent possible. If you've encountered the
Yes.
term. Okay. So we're really talking about an adjacent possible, a wave front of possible innovations. If you look at the history of technology, especially recently, you'll find that almost no innovation stands in the adjacent possible for very long. It's discovered awfully quickly, so that there is no or very few cases where you say, wow, we could have thought of that 20 years ago, right? It's the case that it's only recently that it's become possible, and then people discover it quickly. But, and this is something we do in a tech history class I teach, if you imagine different physical circumstances for our civilization, say, for instance, that we're the size of mice,
Okay.
does that result in a different interest in technology? Oh, yeah. So, for instance, traveling across oceans would be an astonishingly difficult thing when the ocean is effectively, 1,000 times bigger than it is for us, given our relative size. Or what if the atmosphere were very thin? Would we have developed heavier than air flight? No. What if we lived on a planet with a gravitational well like Jupiter? Would spaceflight have been anything we'd have developed by now? No. I think you'd need nuclear power to get a rocket off of Jupiter's surface and get out of that gravitational well. I don't know what the escape velocity is, but it's astronomical. So the physical circumstances of the species you're imagining will determine its technological interests.
Okay, so then let me ask you another speculative question, if I may. So I'm asking you to make a radical assumption for this. It's a big universe, Drake equation, et cetera.
Yeah, we can talk about the Drake equation.
Yeah, so it's a big place. So let's say that there are organisms in existence similar to us. Let's say that they're maybe a little more advanced than us technologically, but not that much more advanced, because I don't want it to,
You don't want to...
balloon up, rocket up. Okay. Let's say that they had basic gravitational conditions that are mostly the same.
Right.
Do you think it would be possible for those civilizations to develop technologically without the advent of the wheel?
Another way to ask it be, would any civilization have advanced that far technologically and not thought of a wheel?
Yeah.
And I think the answer is no. Of course they'd have thought of a wheel. It's a pretty simple idea. Now, I don't know. I suppose we could try imagining cases where they're
So it's a big universe. Do you think it's possible that there's a civilization that's spacefaring civilization that never developed the wheel that's similar to our own?
Okay, so this is a bigger question, and one that deserves looking at closely. The Drake equation is used usually to reach the
Let's talk about that. Define it for us.
Okay, so the Drake equation is taking into account all the different factors that are necessary for an intelligent species to rise. You got to have a habitable planet, right? And you got to have, I've forgotten what all the factors are in it, but it's, how many stars are there? How many of those have habitable planets? How many of those habitable planets have the right balance of water and land, so you could develop in that context? And there are a series of probabilities there. And the argument is made, well, even though they multiply together to make a fairly small probability on a per star basis, God knows there's so many stars, there's got to be intelligent life
Even
elsewhere.
at the most conservative, maybe not the most, but among the most conservative.
Okay. But here's a mathematical problem, and this is something that might be worth thinking about here. It is not true that an infinitesimal multiplied by an infinite results in some finite number. It could be that the infinitesimal is so darn small that even if you multiply it by a vast infinite, you still end up with 0 or 1.
Well, yeah, it
rather
would
than
have
multiple.
to be non-zero.
Yes, well, because we have one example of an intelligent species, we're sitting here. But beyond that, it is not mathematically accurate to say just because there are these many stars, even a very small probability of intelligence will result in an intelligent civilization.
Why?
Because the probability could be even smaller than we think. And in recent years, there have been some publications, I forgot the name of the book, but it's called The Rare Earth Hypothesis. And the idea is that as we look at especially paleontological history, we see a number of gating events on this planet that could have stopped.
Filters, like a great filter.
Yeah, the great filter is used for this notion, and these are filters early on. So, for instance, after a few billion years, plants learn how to oxidize, how to photosynthesize, and they produce oxygen. Damn near kills all life on the planet because you suck all the carbon dioxide and methane out of the air when you do this.
Yeah.
And those are greenhouse gases, and the sun was a lot cooler back then. And the result is we have recently, in the last decade or two, discovered that the entire planet was glaciated for hundreds of millions of years.
Right.
In part due to this depletion of greenhouse gases. And how did life survive that? And right now, the answers are kind of hand-waving. Well, somehow it did because we're here. Well, they don't know how.
No, I'm not a mathematician, but no matter how small the number is, if you divide it by, if you multiply it by infinity, you get infinity.
Well, of course, you're not really talking about infinity with the number of stars.
Oh, okay. Well,
Right.
I guess you'd have to go to
big
parallel.
value.
You'd have to go to the multiverse for that. But
Even then,
okay, well, the moment you limit it
me do
to
it this
something
way for
other
you.
than infinity, then you're right.
let's do an intuitively reasonable argument. Do you think that there is another species in the universe that, in Star Trek style, looks humaniform and speaks English? I mean, literally speaks English. Like, we land on the planet in Star Trek and they're talking English.
Yeah, well, they solved that through the universal translator problem. Farscape
Fine.
solved that through the microbial problem.
And modern Star
okay.
Trek does a little bit of canon.
Yeah.
If I recall in, Bread and Circuses, Spock makes some comment like, this is so parallel, they're even speaking English.
Yeah,
Yeah?
They actually run into, in the episode Darmok, they actually run into species in which speak in only metaphor, and they
Right,
can't be
speak only by
translated.
metaphor,
Darmok,
sure.
Enchilada, Tanagra.
But
Okay,
the question
so,
arises,
yeah.
do you believe that this is realistically possible, that somewhere in the universe there is a humaniform species like us that speaks modern 21st century English, as it turns out?
Well, I think I'm going to answer your question directly, but please give me 20 seconds to expound on that. I do not know. The answer is no.
Okay.
I do not. However, I think if my mentor, Victor Stenger, who was one of my mentors, who was a particle physicist, told me that there's an infinite number of in any possible world that doesn't violate the laws of physics manifests itself. So
Okay, you're
you'd
gonna
have
talk
to go to a multiverse, or you'd have to go out from there. And by the way, I'd like to recommend a show to you. It's fantastic. I'm watching it now. Dark Matter. If you haven't
haven't
seen
it. I'll check it out.
Genuinely excellent. Okay. Anyway, go ahead.
So, okay, you want to go with the multi-world interpretation
Well, no, we don't
of quantum
have to
mechanics.
go.
That's
We
a
don't-
different question.
no. So
Well,
I'll
let's
answer-
stick with ours for now.
Okay. So no, I don't. I think it's so unlikely as to be. I don't want to say impossible, and I know that virtually impossible is linguistically problematic. So no, I don't think it's. I do not think there is one.
So interestingly, what you just said was there is a very small possibility of this
Correct.
occurring, but you don't believe it actually is happening in the universe, despite all the stars that are out there. So what you just said, in fact, was that the thing can be so infinitesimally small in likelihood that even with all the stars it could happen at, it's still not going to happen.
Yeah, that's kind of jerry-rigging the system because you use the word belief. Like if you took the word belief out of there and just said thought, no, I don't think it exists. I certainly don't believe it exists.
And I think mathematically it probably doesn't. So it is possible for an infinitesimal to be so small.
But wait a second. Mathematically, it does.
Well, one. Sorry, you're right. But not two. So it is mathematically unlikely
Mathematically-
that there are two such cases.
It's mathematically what? What's the words that you modified?
I dropped impossible for you. You're perfectly correct. Of course, we're sitting here talking English. That's obvious
But
enough.
it's not impossible. You're saying it is impossible to have another one.
To put it in precise mathematical terms, I've forgotten how many stars there are thought to be in the universe at present. We could look it up, but I'm going to guess somewhere in the order of 10 to the 20th power. Maybe I'm off by a few powers there, but it doesn't matter because if the likelihood of intelligent life is 10 to the minus 21st power, then the chance of those two multiplied together is 10%. All right? And if it's 10 to the minus 24th power,
Oh, I see. Okay,
now
so
it's
you're saying
1 in
it's-
10,000. So
you're
an
saying-
infinitesimal can beat or a very small fraction can beat a very large number.
Yeah, as
just
long
a
as it's
question
not
of
an
how.
infinite number. Okay, so since we're talking about it, something that's fascinated me for a long time. And again, I realize it's out of your area, but if you're not comfortable talking about, we don't have to talk about it. The Fermi Paradox.
Oh, sure.
Where's everybody?
We've already
Where
been
is
heading on that. You were
everybody?
talking about gating events.
Yeah. Well,
Okay,
where is everybody?
So your viewers understand what we mean by Fermi Paradox? We okay with
Tell
that?
us. Tell everybody.
Okay. So the Fermi Paradox, posed originally by physicist Enrico Fermi, noted contributor in the mid-20th century, Manhattan Project, that sort of thing. And he was the first to kind of publicly note that if there is other intelligent life in the universe, we could expect that it is on a different time schedule than us. Maybe it's been around for a little longer. Where are we going to be in 10,000 years?
Well, I can't even imagine where we're going to be in 100. So
Right.
yeah.
And it's reasonable to expect that we'd be exploring the cosmos in some way or another in 10,000 years. If they got to start even 10,000 years earlier than us, they're exploring the cosmos, right?
We got to come back to that question. I've literally had a change of mind after talking to the physicist David Deutsch about that, and after talking to people about psychedelics. Okay, but anyway, run with it.
Sure. So the argument then is, why aren't they here?
Yeah.
Because they would long since have come if this is at all possible. It's unreasonable to expect that they would have started their tech development at exactly the same time we did.
Right.
There must have been ones that have been around for maybe millions of years. So it stands as an ongoing question for decades now, and it is called the Fermi Paradox. There are a lot of answers to it.
What's
Some of
yours?
them very darkly dystopian, some of them.
Yeah.
There's just something we'll discover, and in a little while we'll figure out how to make a absolutely lethal virus you can make in your basement, and some clown will do that and kill us all. And that's how civilization eventually ends. I'm a little more of an optimist. I think what we're discovering, in fact, is that this planet is extraordinarily rare. There's a whole combination of things you need. It isn't just survive the photosynthetic crisis. It's you got to have plate tectonics, which we didn't even know about when I was a boy. If you don't do that, then all your carbon gets lost to the crust, and it doesn't get recycled. So you have to have plate tectonics.
Yeah.
The habitable zone, there is no habitable zone. The star changes its intensity throughout its entire life. So what constitutes the right distance from the sun is different now than it was a billion years ago and a billion years before that. And you got to have a balanced system that has the right greenhouse gases to keep you warm enough as the sun's intensity changes. It's become clear, for instance, that I think it's another 500 million, maybe billion years, this planet will be uninhabitable. Because as the sun increases its intensity, the reduction in greenhouse gas will not be sufficient to keep the temperature reasonable on the surface.
So you are a great filter guy then. I mean, that's
Sure. I just think the great filter's already been passed. I think we're probably alone. And the reason is we haven't found anybody else, even after careful looking. And it's increasingly clear that what it takes to have gotten where we are is not as easy as we thought. And every time we turn around, there's another fundamental requirement necessary for life to have evolved to the point it has. So it may well be that the Fermi Paradox answer is, sorry, there is nobody out there, it's us.
Yeah, years ago I was thinking about writing a paper on many of the cultural variables that go into the Drake equation. So, for example, when sustainability was hot, people were talking about putting that in, or nuclear war. That when people are talking about putting that in, so we are informing the Drake equation as we go along. I don't know. I have a different perception, and we spoke before about something that I was talking to Shermer about that just completely blew my mind. When Nick Bostrom said that he gives the likelihood that we're in a simulation to be over 50%. And, Shermer said, and he's right, he got that through Bayesian reasoning. And I said, well, that's a good reason to throw Bayesian reasoning out the window, because that's I don't want to say it's an insane conclusion, but it's a conclusion that, that'd be an example of what you said about the starting axioms. If that's your way of reasoning to the world, well, then 50% would seem like, 50%.
Well, first of all, human history is full of conclusions that at the time seemed insane.
Yeah.
For instance, if you try to convince a medieval person that the sun is not revolving around the earth, but rather we're turning on our own axis,
that's
his reasonable
right.
answer is going to be, well, I'm looking at it, it's coming up in the east.
I didn't want to say
we're turning
insane,
on our
but
own axis? What do you mean? We got to be moving at 600 miles an hour for that to happen. If he's enough of a mathematician, he can figure that out. I don't think we're moving at 600 miles an hour, do you? Looks pretty stupid.
Yeah, Wittgenstein said, how would it look if the Earth, if the sun revolved, like how would it look differently? Okay, so
it sounds counterintuitive. Is not a conclusive argument. Sorry.
Yeah, no,
and Bayesian mathematics, by the way, is precisely and mathematically correct. It's a powerfully useful tool.
Okay, so
I
let's
suggest his
explore this.
application is wrong. I don't think he's right.
Okay, yeah, tell me that. Tell me why. Go ahead,
So
please.
first, let's go through his reasoning process. What he's saying is that assuming we reach, as seems possible, a condition where we will be able to create fully realistic artificial intelligences, what has lately been termed AGI, artificial general intelligence, behaves like a full human being, right? Then that means we'll be able to build such programs to model people. Right? And then in turn, we might be very interested in that future in building what amounts to a historical video game of sorts and creating a bunch of people. Maybe I'm real interested in, I don't know, the American Revolutionary period. So I set up in my supercomputer of the future 3 million artificial intelligences. This is about the population of the colonies at the time. And I run them. And they think they're in 1775. And how can they tell the difference? You know, it's like being in the Matrix, right? How do you know whether you're really in that simulation or not? And given the huge likelihood that that would happen, that so many such simulations would be created, a kind of mathematics called Bayesian reasoning, it's not too hard to explain. The question is, well, we're here talking. It could be because we're the real people, right? There's one chance of that. But if really there are millions of simulations, the odds are that the explanation of why we are here is more that we're one of those millions than that we're the one.
What do you think the problem with that reasoning is?
Okay. So this ties into the bigger question of the hard problem of consciousness and what we should do if we do arrive at such entities and how we will treat them. Okay? Are they self-aware? That's the critical question. I think we would mostly agree, any reasoning moral person would say, well, if we've created an entity that has feelings and sentience, we have to treat it with the same compassion we would one another.
No, but we don't treat cows like that. We don't treat.
Yeah, but cows don't talk with us in full idiomatic English and express emotions and feelings exactly as humans do. And we still treat cows as, to use the philosophical term, moral patients. You're not allowed to torture them. So even as simple an entity as an animal, we recognize moral obligations to. If we had an artificial intelligence of our level that we could talk to, let's use our Star Trek example here, Data the android, right?
Yes, the measure of a man.
Yep, I was just going to cite that. And it's one of the compelling science fiction representations of this question. Those not familiar with it, Data the android, who everyone loves in the show, he's a
If
marvelous
they're not familiar
character.
with it, they're dead to me. Yeah. So go ahead.
It's a trial to determine whether or not this artificial intelligence, which behaves very humanly, is a human being or not, has rights. Or can he just be disassembled because a fellow wants to study him, and is he a non-entity, at least not self-aware? So that's the question we might have to answer in the model that Bostrom is talking about. If we get that far, we're going to have to decide how to treat these entities, right? I would argue that deciding whether they are self-aware or not is unanswerable. We can't do it for ourselves. After millennia of attempting, we can't provide a conclusive ontological result, a result that determines the reality of the thing. I think we could argue that it is either true or not that these things are sentient, but we can't prove it. So I would argue that the philosophical question is not ontological, it's ethical. And the question is, how should we act?
And is your argument that we should defer to the side to kind of take a weird version of the precautionary principle? Like you should we should defer to it being conscious, and so
Okay, better safe than sorry.
Extend ethical obligations to it.
Certainly that's the way we work right now, isn't it? I can't prove that you're self-aware, you can't prove I am, but neither of us is going to say, well, he's just a thing, I can kill him.
Thank you. Appreciate that.
And
or Reed, too, over there.
Yeah, precisely. So
Because Reed's looking pretty good for dinner right about now.
I'm not going to give you my own answer to it. I have a fairly strong opinion, but I want to stay neutral because when I teach classes, I don't want to be on record as having one opinion or another. I want my students to be able to debate.
I totally understand. I think that's actually really important, yeah.
But I'll tell you what will happen. I think we're going to go with the model you said.
Okay.
And if you look at the sweep of cultural views of robots over the past 100 years, the trend is unmistakable. The robot in Metropolis, 1920s, is a strange alien.
Super cool.
No one's talking about it being a human, though.
Yeah,
There's a
Lost in Space, you remember that?
Sure, and that's the
Danger
first
Will
time the robot
Robinson.
begins to be likable.
Yeah,
He's kind of the
yeah.
family dog,
Yeah.
but he's still somebody you care about.
Yeah, yeah.
There's a marvelous Twilight Zone episode called The Lonely.
That was great.
know that episode?
Yeah, of course I do.
Okay, and so that produces this very, very delicate balance. Is the female robot that is his companion really a sentient being?
Yeah.
Or is he looking in a mirror? Yeah. And so the point is that there's this evolution from the robot being the alien, the robot as they called it back then, was the pronunciation of the word, to data in Measure of a Man. And you watch Measure of a Man and everyone is rooting for data.
Right.
There's no question about it. You can argue philosophically all you like. I think what's going to happen is when these entities, if they get to that point, are that human, we're going to treat them as human. Just watching the cultural evolution that's going on here. Yeah. It isn't going to be an abstract result. It's going to be a gut feel. And it's heading in that direction. Hold on now.
Yeah, please.
Okay. So now, we got these things. We've decided that they are to be treated as human. You want to create 3 million of them and make a simulation out of them? What you're saying, in effect, is I'm going to create 3 million people and run a simulation with them. Well, I'm sorry, they have rights. And the very question of being able to spontaneously create new intelligences by what amounts to a copy and paste is going to be a challenge, especially if our agreement, because of the way things are heading, is that we need to treat them as moral patients, as things that have rights.
I see. I thought you were going to make a link to Bostrom and then...
Well, I'm going to make a link to Bostrom.
Okay.
Which is, the argument is that you're not going to be allowed to create people in simulations unless you get informed consent, in which case, it's like, okay, we just created you and you're a simulated entity, but you have awareness. We'd like to run you in the 18th century here, please. Are you okay with that? And whether I say yes or no, I am aware that I'm in a simulation.
Okay, well then I'm going to ask you a direct question, and I'm going to ask you for a number. How likely is it, do you think, we're in a simulation?
Well, there's going to be that series of probabilities, right? And the question is, how likely would a future civilization, if it exists capable of this, be willing to take sentient artificial intelligences, which we would be, and put them in a simulation without even consulting them on the matter?
So the way that you would figure that out is through Bayesian reasoning.
Yeah, and I think the actual likelihood is pretty low.
Wow. Oh, so wow, that's super interesting to me. So
not because they couldn't do it.
Yeah.
They wouldn't do it. It's unethical.
Oh, that's interesting. Okay. Well, this has been a fascinating conversation, and we went over, and you've been very generous with your time. I appreciate it.
Thank you.
Is there anything I should have asked you that I didn't ask you?
Well, where we're heading with the AI is always an interesting question I get asked, and we didn't have a chance to talk about that. Will it get to the point of being artificially intelligent is a whole area that deserves a lot of interesting discussion.
I'll be back in January, so maybe we'll continue the conversation about that I'd love that, about that very topic.
Sure.
Where can people find you and your work?
Well, I work right now at Principia College. I'm a professor of computer science there. Clint Staley at gmail.com. Easy way to reach me. It's my personal email. And I'm a big supporter of UATX and hope I might be able to contribute as a faculty member sometime in the future.
We'd love that. Hey, real quick, before you go, top 5, and then I'll answer this question myself, top 5 science fiction shows.
Wow. Can I use written as well as shows?
No, it has to be shows.
Has to be shows.
All right, go ahead. Use written. Written. Okay.
So, Measure of a Man strikes me as an important one.
I meant.
Shows period?
Yeah, shows period, not episodes. Yeah,
and you're talking about TV series.
I'm sorry. Yeah.
I'm
top
going to vote
5.
pretty high on Star Trek.
Okay.
I was raised on TOS, the original series, but I think TNG is superior.
Okay.
TOS is still pretty good.
Okay. We'll add that into our next debate. Okay, keep going.
Oh, gosh, you're catching me on the spot here. I'm trying to think. Firefly was a kick. I loved the Western science fiction combination. It was fun. TV science fiction shows. Star Trek still stands out to me. How about you? What do you like?
Farscape.
Haven't had a chance to look at it.
It's genius.
Yeah. Okay.
Blake 7. If you haven't watched Blake 7, it's genius. Babylon 5.
I've heard about Babylon 5.
Okay, dude, that show is mandatory.
Okay.
Like that's so profound I can't even begin. But we've got to wrap it up, and Reed is looking like he's going to drop dead.
I'll drop
over
in
there.
one for the science fiction side, the written side. Bicentennial Man.
I've seen it.
Isaac
It's great.
Asimov.
Yeah, it's
Well,
great.
the movie is one thing. The novel is another.
I haven't read the
Of course,
novel.
It was a novella. It's an excellent discussion of this whole question of the humanity of robots or artificial intelligences, and it's in the mid-1970s, so it's quite ahead of its time.
Excellent. Thank you so much. I appreciate
you.
you being on the
Nice
show.
talking.
Thank you. Thanks for watching. Be sure to subscribe and hit the notification bell. This falls under the umbrella of my nonprofit, National Progress Alliance. Your generous donations keep us going and help fuel content like this. We truly appreciate your support. Thanks again, and we'll see you in the next one.